We live in a world in motion, literally. As you're watching this video, you might be sitting in a chair, but you're moving. As you sit in your chair, the planet is rotating on its axis. It's also revolving around the sun. But the sun is moving too. The sun is moving through the Milky Way galaxy. But the Milky Way galaxy is moving too. Ultimately, we are in motion always, and it's extremely complicated. In this unit, we're going to focus on the motion of projectiles. A projectile is any object that's in motion that's influenced by gravity. Our goal here is to quickly be able to find angles and distances needed to fire a projectile so that we can shoot at other people's battleships. What? Yeah, that's right. This unit, we're building battleships. But before we get there, we need to start simple. We'll start with one-dimensional motion. We also call this linear motion. We'll focus on two dimensions, the y dimension, or the up and down dimension, and the horizontal dimension, or the side to side, left to right, x dimension. So let's think about the x dimension first. Let's say we have a guy that's standing 5 meters away from a wall. His distance is 5 meters. Distance is the measure of the space between 2 points. In this example, the wall is what we call our reference point. It's fixed. We could also call it our 0 point. Let's say the man walks away from the wall to a new distance of 8 meters. 8 meters is his new distance from the wall, but how far did he move? He moved 3 meters. We call this his displacement. Displacement is a fancy word for a change in location, and it's important that it includes a direction. Displacement is what we call a vector quantity, meaning it's a number with a direction. So we would say that his displacement is 3 meters to the right. Let's say he moves for 5 seconds. How fast did he go? For this, we need to calculate speed, or the average change in position over time. The equation for speed is very simple. It's s equals d over t. So in this example, s equals d over t would mean that the man went 3 meters in 5 seconds. So he'd have a speed of 0.6 meters per second. Speed is a scalar quantity. A scalar quantity is just a number. It doesn't have a direction with it. Mass is an example of scalar quantity. So speed is a number without direction. The vector version of speed is called velocity. So the velocity of the man was 0.6 meters per second to the right. With this calculation, we assume that the man moves at constant speed or at a steady rate. There's no acceleration.
Let's look at an example problem. Let's say that a track runner runs 25 meters at 8 meters per second. How long will it take for him to reach the finish line? Well, we know that speed is equal to distance over time. We can get time out of the denominator by multiplying it on both sides. If we do this, we get d equals s times t, but we still don't have t by itself. So if we divide both sides by s, we'll get an answer of 3.125 seconds.
But in the real world, people don't move at constant speed. So what can we use if we use real people? That's where acceleration comes in. Acceleration is the rate that the velocity changes over time. In this class, we're going to assume that acceleration, when it's there, is always constant. Non-constant acceleration gets a little crazy, so we'll come back to that in a later class. The equation for acceleration is a equals delta v over t. Delta v means change in velocity. So you take the final velocity and subtract the original velocity.
Let's look at a problem in the y dimension. Suppose a baseball is dropped from rest and its final velocity is measured to be 15 meters per second down, or negative 15 meters per second. How much time did it take for it to fall? Well, the Earth accelerates all objects in the air at negative 9.8 meters per second squared. It's negative because the Earth pulls the ball down. A equals delta v over t, and delta v equals v minus v naught. And since v naught is 0 at rest, it goes away. That leaves a equals v over t. To get t, we multiply it on both sides. Then we divide both sides by a, so that t equals v over a. If we plug in our information, the negative signs cancel and t equals 1.53 seconds.
One-dimensional motion is pretty simple. Those are the two equations that you mostly need to get out of trouble. But you might need two more complicated versions in case you need to solve for something specific. In our next video, we'll need to combine the x dimension and the y dimension to understand how projectiles work.